Hello everyone, welcome to the lecture on entity relationship or ER modeling. In this lecture, we will learn the main characteristics of entity relationship components, how relationships between entities are defined, refined, and incorporated into the database design process, how ER components affect database design and implementation. And also, we shall learn that real-world database design often requires the reconciliation of conflicting goals. The entity relationship model, or ERM, they may also sometimes refer to as ERD, entity relationship diagrams. ER model forms the basis of an ER diagram. Entity relationship diagram represents the conceptual database as viewed by any user. Entity relationship diagrams depict databases' main components, entities, attributes, and relationships. Because an entity represents a real-world object, the words entity and objects are often interchangeably used in relation to ERM or ERDs. Entities. The word entity in the ERM often is corresponded to a table. The ERM refers to a table row as an entity instance or entity occurrence. Entities refers to entity set and not a single entity occurrence. Corresponds to a table and not a row in the relational environment. Entity name is a noun and is often written in sentence characters in uppercase letters. Attributes, characteristics of entities. Attributes represented by ovals connected to entity rectangle with a line. Each oval contains the name of attribute it represents. Attributes are in general characteristics of entities. For example, the student entity may include student last name, student first name, and student initial. These are attributes of the student entity. The illustration shows an example of Shen and Cross foot model in formulating an entity relationship model. The one on the left represents Shen model, and the one on the right reflects that of Cross foot model. Attributes, required attributes. A required attribute is an attribute that must have a value. In other words, it cannot be left empty. As shown in the previous figure, in the previous slide, there are two bold-faced attributes. Refer to the one on the right-hand side. This indicates that a data entry will be required. In this example, student last name and student first name require data entries because of the assumption that all students have a last and a first name. But students might not have a middle name, and perhaps they do not yet have a phone number and an email address. Therefore, those attributes are not presented in boldface in the entity box. An optional attribute is an attribute that does not require a value. Therefore, it can be left empty. Ideally, an entity identifier is composed of a single attribute. However, it is possible to use a composite identifier, that is, a primary key composed of more than one attribute. Attributes are classified as simple or composite. A composite attribute, not to be confused with a composite key, is an attribute that can be further subdivided to yield additional attributes, such as city, zip, and street. A single value attribute is an attribute that can only have a single value. For example, a person can only have one social security number, and a manufactured part can only have one serial number. Multi-valued attributes are attributes that can have many values. For instance, a person may have several college degrees, and a household may have several phones, each with its own number. In the ER model in figure 4.3, the car entity's foreign key has been typed as mod_code or model code. This attribute was manually added to the entity. Actually, proper use of data modeling software will automatically produce a foreign key when the relationship is defined. In addition, the software will label the foreign key appropriately and write the foreign key's implementation details in a data dictionary. Therefore, when you use database modeling software like Visio Professional, never type the foreign key attribute yourself. Let the software handle that task when the relationship between the entities are defined. Attributes. Although the conceptual model can handle many-to-many relationships and multivariate attributes, you should not implement them in the relational database model in models. So if multi-valued attributes exist, the designer must decide on one of two possible courses of action. First one, within the original entity, create several new attributes, one for each of the original multi-valued attributes components. The second option, or course of action, is to create a new entity composed of the original multi-valued attributes components. This new entity allows the designer to define the color for different sections. Finally, an attribute may be classified in a derived attribute. A derived attribute is an attribute whose value is calculated or derived from other attributes. The derived attribute need not be physically stored within the database. Instead, it can be derived by using an algorithm. For example, an employee's age may be found by computing the integer value of the difference between the current date and the employee date of birth. Relationships. Relationships between entities often operate in both directions. That is, to define the relationship between the entities named customer and invoice, you would specify that a customer may generate many invoices. Each invoice is generated by one customer. Because you know both directions of the relationship between customer and invoice, it is easy to see that the relationship can be classified as one-to-many. The relationship classification is difficult to establish if you know only one side of the relationship. For example, if you specify that a division is managed by one employee, you don't know if the relationship is one-to-one or one-to-many. Therefore, you should ask the question, can an employee manage more than one division? If the answer is yes, the relationship is one-to-many. And the second part of the relationship is then written as an employee may manage many divisions. If an employee cannot manage more than one division, the relationship is one-to-one. And the second part of the relationship is then written as an employee may manage only one division. Connectivity and cardinality. The entity relationships may be classified as one-to-one, one-to-many, and many-to-many. The term connectivity is used to describe the relationship classification. Cardinality expresses the minimum and maximum number of entity occurrences associated with one occurrence of the related entity. Connectivities and cardinalities are established by very concise statements known as business rules. Such rules derived from a precise and detailed description of an organization's data environment also establish the entity relationship models, entities, attributes, relationships, connectivities, cardinalities, and constraints. Because business rules define the entity relationship models components, Making sure that all appropriate business rules are identified is a very important part of a database designer's job. As we examine figure 4.7, keep in mind that the cardinalities represent the number of occurrences in the related entity. For example, the cardinality 1 and 4 in brackets written next to the class entity is the professor in the professor teaches class. Relationship indicates that each professor teaches up to 4 classes, which means that a professor table's primary key value occurs at least once and or more than 4 times as foreign key values in the class table. If the cardinality had been written as 1, n, there would be no limit to the number of classes a professor might teach. Similarly, the cardinality written next to the professor in 1, 1 indicates that each class is taught by one and only one professor. That is, each class entity occurrence is associated with one and only one entity occurrence in professor. Existence dependence. An entity is said to be existence dependent if it can exist in the database only when it is associated with another related entity occurrence. In implementation terms, an entity is existence dependent if it has a mandatory foreign key, that is, a foreign key attribute that cannot be none. For example, if an employee wants to claim one or more dependents for tax withholding purposes, the relationship employee claims dependent would be appropriate. In that case, the dependent entity is clearly existence dependent on the employee entity because it is possible for the dependent to exist apart from the employee in the database. If an entity can exist apart from all of its related entities, it is existence independent. Then that entity is referred to as a strong entity or regular entity. Therefore, existence dependence is entity exists in database only when it is associated with another related entity occurs. For example, your business rules might dictate that an entity must be associated with a name. Relationship participation. Participation in an entity relationship is either optional or mandatory. Optional participation means that one entity occurrence does not require a corresponding entity occurrence in a particular relationship. Mandatory participation means that one entity occurrence requires a corresponding entity in a particular relationship. Developing an entity relationship diagram. The process of database design is an iterative rather than a linear or a sequence process. The verb iterative means to do again or repeatedly. An iterative process is thus one based on repetition of processes and procedures. Building an entity relationship diagram usually involves the following activities. Create a detailed narrative of the organization's description of operations. Identify the business rules based on the description of operations. Identify the main entities and the relationships from the business rules. Develop initial entity relationship diagram. Identify the attributes and the primary keys that adequately describe the entities. Revise and review the ERD. Database designing challenges, conflicting goals. Database designers often must take design compromises that are triggered by conflicting goals, such as adherence to design standards or design elegance, processing speed, and information requirements. Design standards. The database design must conform to design standards. Such standards have guided you in developing logical structures that minimize data redundancies, therefore minimizing the likelihood that destructive data anomalies will occur. You have also learned how standards prescribe avoiding nulls to the greatest extent possible. In fact, you have learned that design standards govern the presentation of all components within the database design. In short, design standards allow you to work with well-defined components and to evaluate the interaction of those standards with some precision. Without design standards, it is nearly impossible to formulate proper design process, to evaluate an existing design, and to trace the likely logical impact of changes in design. Processing speed. In many organizations, particularly those generating large number of transactions, higher processing speeds are often a top priority in the database design. Higher processing speed means minimal access time, which may be achieved by minimizing the number and complexity of logically desirable relationships. If the focus is on data retrieval speed, you might also be forced to include derived attributes in the design. And finally, information requirements. The quest for timely information might be the focus of database design. Complex information requirements may dictate data transformations, and they may expand the number of entities and attributes within the design. Therefore, the database may have to sacrifice some of its clean design structures and or some of its high transaction speed to ensure maximum information generation. To sum up, it is important to meet logical requirements and design conventions. Design is of little value unless it delivers all specified query and reporting requirements. Some designs and implementation problems do not yield good solutions. Therefore, a keen attention must be taken and given to it. To summarize this lecture, entity relationship or ER model uses ERD to represent conceptual database as viewed by end user. Entity relationship models' main components are entities, relationships, and attributes. It also includes connectivity and cardinality notations. Connectivities and cardinalities are based on business rules. Many-to-many relationships is valid at conceptual level, must be mapped to a set of one-to-many relationships. Entity relationship diagrams may be based on many different entity relationship models. Unified modeling language class diagrams are used to represent the static data structures in a data model. Database designers are often forced to make design compromises. This finishes the lecture notes on entity relationship models. Thank you.